In this video, we will discuss and evaluate the Constant Velocity Lab. There are three main objectives in this lab: to record and analyze the motion of an object moving with constant speed in one direction, to create a computational model describing the object's motion, and to compare the observed motion to the predicted model. We will need two key concepts: Newton's first law, which states that an object under constant motion must maintain that motion unless acted upon by an unbalanced or outside force, and Newton's second law, or the momentum principle, which states that net force is equal to the change in momentum over the change in time, where momentum is equal to mass times velocity. So let's take a look at our object in motion. Here is a screenshot of our ball and tracker. Because we only needed to evaluate a few frames of motion, a shorter clip of the ball's motion was used in tracker, meaning we needed to adjust our initial position and initial velocity. So in our code, lines 33 and 34 change the ball's position and velocity according to tracker. In line 38, time is analyzed at 1/30th of a second. In line 52, there is no net force acting on the ball, so our net force vector is equivalent to 0, 0, 0. In line 56, velocity is changed using the velocity update formula, which states that final velocity is equal to initial velocity plus acceleration times time, as pictured below, where acceleration is replaced by net force over mass. But because our net force is 0, that cancels out mass, and we just add our initial velocity to the 0 vector. In line 57, position is changed using the position update formula below, which states that final position is equal to initial position plus average velocity times the change in time. Now we have a table of the ball's position at each time frame and then those values graphed on the left. On the right, we compare observed position versus the computational model position. The results showed that position is directly proportional to time in the absence of an outside force. The predicted change in time was 0.1 seconds, however, the experimental change in time is 0.33 seconds because tracker evaluates the frames of motion in a 30th of a second, so the experimental motion was evaluated at a greater number of frames than the predicted motion in the same amount of time. Thus, more data points were plotted. My model was a yoga ball of a 0.75 meter diameter and a 0.92 kilogram mass. There was a large initial velocity of 1.87 seconds because the ball could cover more ground in less time due to its size. The computational model shows a linear relationship between position and time with slight deviations. The deviations were due to human error when placing the center of mass by hand on tracker. This caused some positions to vary from the mean slightly. Air resistance and friction caused the ball to slow down, leading to a slight decrease in its motion on the graph. So what if axis orientation was different? Would there be any differences within the computational model or any similarities? If axis orientation differed, essentially there would be no change in the computational model. Because there is a positive linear relationship between the two, that relationship would remain by switching axes and the slope would still be positive. So let's go deeper and take a look at the graph pictured. For example, when we plot the graph for the equation y equals 2x, since we will be putting values in x to get values of y to plot, the x values go on the x-axis and the y values go on the y. But if we rewrite the equation as x equals y over 2, now we will be putting values in y to get the values of x, and the process is inversed. I've added a +2 to distinguish between the two graphs so that we may evaluate them both more easily. But as you can see, with the change in axis orientation, the two graphs remain the same. Ultimately, the computational model would also remain the same. So is it possible to determine the quantity of outside forces that amount to 0 net force? According to Newton's second law, an object could still be in constant motion even with forces acting upon it. This is because those outside forces would cancel each other out. However, for this lab, it is not possible to count the number of outside forces that would amount to 0. Because of imperfect conditions, we can only assume any outside forces that may have affected the motion of our object, and even then, we have no way of making accurate and precise calculations for such. Thus, we can only make an educated inference as to how many outside forces amount to the 0 net force, but we cannot state anything with absolute certainty. And now we have successfully recorded and analyzed the motion of an object moving with constant speed in one direction using Newton's first and second laws. We have used the position update equation and the velocity update equation, created a computational model describing the object's motion, and compared the observed motion to the predicted model.